Good afternoon. Today I spent a lot of time trying to figure out the essence of the partial derivative of a tensor. Now that has mostly resulted in confusion, but hopefully I've managed to pull a tiny bit of clarity out of that confusion and we'll be able to distill it into this video. I'm going to start by referring to time 5730 from Dr. Physics A's video where he asks this question. He asks whether these two expressions are equal to one another. Now to me, this term over here on the left appears to be the transformation of a differential change in a vector field from x-coordinates to y-coordinates. On the other hand, this thing over on the right is the derivative of a vector field. Now today I was unable to come up with any reason that these two things should be the same, but then I started looking at this notation on the left and just using commutation where commutation probably shouldn't be used, and I started to see some justification for expecting them to be the same. So first I'm going to copy this down where I can see it better. Next, I'm taking this partial and this partial y, putting them over here, and taking this partial x, partial y, and putting it right here. And finally, of course, the v sub r goes right there. Now, I don't think you can do any of that. You can't just break apart a partial differential operator and put something between it and its operand. I mean, you can do whatever you want, of course, but if you want to start with, if you want the thing you started with to be the same as the thing you end with, you shouldn't do that. So, no, of course not. On the other hand, though this is definitely not equal to this or this second equal sign actually is correct. This part and this part is a version of the equation I was calling equation 1 twice. This equation was introduced at time 4730 in Dr. Physics A's video. This was equation 1. And this is equation 1 twice. So what I'm going to do is show that these parts that I've put blue rectangles around is essentially identical, except for different variables, to equation 1 twice. I think there is going to be a more fundamental difference, though. Just like I've been complaining that Einstein notation plays fast and loose with commutativity, here there's going to be a difference that's based on associativity. I'll change this equation first by converting all the x's to y's and the y's to x's. Then I'll change all the y superscript m's to dv subscript m's. Or v sub x. This is v sub y. V of x. V of x. V of y. And I really don't care about the dummy subscripts m and r. They're dummy variables anyway, right? Now you can see perhaps why I keep getting confused. As soon as I start trying to use the Einstein notation, it screws me up. So I'm just going to erase this step altogether and leave this as it is, but erase this one and put x on the top and y on the bottom. Now, there's something that I'm currently finding counterintuitive, that dx got converted to dv of y, and that dy got converted to dv of x. Perhaps this has something to do with contravariant and covariant forms, which I have not yet been able to grasp. In any case, I just want to talk for a second about the simple form of this thing before I talk about the transformation of it, and then I want to talk about the transformation of it. This thing of what I am speaking. We talked about a path element, dx dy. That's a vector, a teeny tiny little vector. Now we've got this thing, dv sub x, dv sub y. And I should point out here that I'm switching gears here. No longer is x a set of coordinates and y is another set of coordinates. I've been thinking of x and y as a pair of Cartesian coordinates, and we could have dr d theta be, for instance, a pair of polar coordinates, and dv sub r, dv sub theta be a pair of polar coordinates. Sorry, I meant r and theta. R and theta are the coordinates. Dr and d theta are differential changes in those coordinates. Similarly, v sub x of x comma y and v sub y of x comma y would be a vector field, while dv sub x and dv sub y would be some differential change in that vector field. If I'm going to talk about a differential path element, dr d theta, that seems to have some kind of intrinsic meaning. But does it? If I talk about dx dy, generally it means somebody, somewhere, is going a little distance dx to the east and a little distance dy to the north. But does that dx dy really have any intrinsic meaning without a starting point, an ending point, or an ending point, or with that somebody somewhere? The situation becomes even more dramatic with dr d theta, because the size of d theta varies drastically with r. I could have the same d theta, but over here, that's just a little bitty distance, and over here, it's a great big distance. So I'm making the case that mathematical entities like dr d theta and dx dy are kind of context dependent. I'm really trying to find a good transition into this. I may or may not have succeeded, but by itself, dr d theta is an ambiguous concept. But once we put another variable on the bottom, what the change is with respect to, then it becomes, I don't know, more explicit. Now, we also have this dv sub x, dv sub y vector field, and it too can be expressed similarly. I'm going to do it this time with a matrix multiplication, del x, del y, turned into an outer product, v sub x, v sub y, equals del v sub x, del v sub y, no, del v sub x, del x, del v sub x, del y, del v sub y, del x, and del v sub y, del y. Now this vector field could be about anything: a magnetic field, a gravitational field, an electric field, the velocity field for a swirling current of water. As long as it has a definite magnitude and direction in the x and y direction at every point in space, then it can be represented by a vector field. But some fields can be represented more easily in one coordinate system than another. Gravitational fields, for instance, can be expressed most easily in spherical coordinate systems around the relevant mass. Magnetic fields may best be expressed in cylindrical coordinate systems around a current-carrying wire. But it may be useful to take the vector field from one coordinate system, where it is easily expressed, to another coordinate system, where it is more compatible with a problem that you are doing. Unfortunately, it may not always be possible to change from a coordinate system of v sub x of x comma y comma v sub y of x comma y to a coordinate system of v sub r of r comma theta comma v sub theta of r comma theta. It might not always be possible to do that, but it does appear we've got a general method of going from dv sub x comma dv sub y to dv sub r comma dv sub theta.